Have you ever stopped to think about what you, your desk, the air you're breathing, and, I don't know, the most distant star in the universe all have in common? Well, the answer is both unbelievably small and surprisingly simple. It's all atoms. And today, we're going to break them down.
It's a huge question, right? I mean, it sounds like it should have some ridiculously complex answer. But here's the amazing part. The core rules that build literally everything we can see and touch are hidden inside the simple structure of a single atom.
So this little diagram right here, this is going to be our roadmap. It all comes down to the three key players you see here. The ones all packed together in the center, that's the nucleus, and the ones zipping around on the outside. If you can understand them, you can basically understand how everything works.
All right, so let's meet the three subatomic particles that build our entire reality. You've got the proton, the neutron, and the electron. That's the whole team.
Okay, first up is the proton. Just think of the proton as the atom's soul. It's got a positive electrical charge, and it lives right at the heart of the atom, in the nucleus. But here's the most important thing. The number of protons is the atom's unique, non-negotiable ID card. It defines what element it is, period.
Hanging out with the proton in the nucleus is the neutron. The neutron is kind of like the proton's chill cousin. It has no charge at all. It's totally neutral. Its main job is just to add mass or weight to the atom. It gives it some heft.
And finally, zipping around that nucleus, you've got the electron. Electrons are these tiny, negatively charged particles. You could say they're the atom's personality. Their number and how they're arranged determines what other atoms it'll interact with and, as we're about to see, its overall electrical charge.
So, let's start with the big one, the particle that tells an atom what it is, the proton.
This rule is absolute. It's non-negotiable. An atom with 8 protons is always an atom of oxygen. If it had 7, it'd be nitrogen. If it had 9, it'd be fluorine. You can change other things about an atom, but the second you change the number of protons, you've changed the element itself. The proton count is everything.
Okay, now that we've got identity locked down, let's talk about weight. How do we figure out how heavy an atom is? Well, the answer is packed right into that dense little nucleus. The formula for this could not be any easier. You just add up the number of protons and the number of neutrons. That's it. The electrons are so incredibly tiny that their mass is basically zero, so we just kind of ignore them for this calculation. All the weight is in the middle.
Let's apply this to our oxygen atom from before. We know it has 8 protons, and the model shows it also has 8 neutrons. So you just do the math. 8 plus 8 gives us a mass number of 16. The unit we use is just called atomic mass units, or AMU for short. See, it's really that straightforward.
So what happens if we mess with the recipe a little? Let's say we toss in 2 more neutrons. Does the identity change? Nope. It's still oxygen, because it still has 8 protons. But the mass definitely changes. Now we'd have 8 protons plus 10 neutrons, giving us a new mass of 18 AMU. We've just made a heavier version of oxygen, which has a cool name, an isotope.
All right, we've totally nailed identity and mass. Now for the most exciting part, in my opinion, the electrons and how their behavior gives an atom an electrical charge. This is where all the chemistry really happens.
So by default, atoms like to be neutral. They want to have a perfect balance. And that means for every single positive proton they have in the nucleus, they have 1 negative electron in orbit. In our oxygen model, we've got 8 protons and 8 electrons. 8 positives, 8 negatives, they cancel each other out perfectly. The net charge is 0.
But atoms can lose or gain electrons, and that's when things get interesting. Let's say our neutral oxygen atom loses 3 of its electrons. Now, the 8 positive protons in the nucleus are still there. They're locked in. But now there are only 5 negative electrons flying around. The positive charges now outnumber the negative ones by 3, giving the atom an overall charge of positive 3. And you guessed it, it works the other way too. What if our neutral atom gains 2 extra electrons from somewhere? Well, the 8 positive protons are still there, but now they're being orbited by 10 negative electrons. Now the negative charges have the upper hand, giving the atom a net charge of negative 2. And any atom that has a charge, positive or negative, is called an ion. So there you have it. 3 particles, 3 simple rules. Protons give you identity, protons plus neutrons give you mass, and the tug-of-war between protons and electrons gives you the charge. Let's put that knowledge to the test. Okay, let's use our rules to fill out this chart. First up, manganese,
or Mn. The chart says it has 25 protons. Rule 1, right? That means its atomic number has to be 25. Simple. The number of electrons is also 25, so the charges are balanced, it's neutral. For the mass number, we just add protons and neutrons. 25 plus 31 is 56. Done. Next, gold, Au. Mass number is 199, and it has 79 protons. So its atomic number is obviously 79. Since it looks neutral, the electrons have to match the protons, so that's 79 too. To get the neutrons, we just work backwards. 199 minus 79 leaves us with 120 neutrons. Easy. And finally, an ion. This is calcium with a positive 2 charge. See that little +2? That's the clue. It has 20 protons, so the atomic number is 20. For neutrons, we do 41 minus 20, which is 21. Now for the electrons. That +2 charge tells us it has 2 more positive protons than negative electrons. Since it has 20 protons, it must have only 18 electrons. And that's it. That's how these 3 rules work together to describe literally any atom in the universe.
Think about it. Everything from life-saving medicines to the smartphone in your pocket exists because we figured out how to understand and manipulate these 3 tiny particles. We've just decoded the basic blueprint for reality. So the real question isn't just what these rules build, it's, now that you understand them, what will you build?